familiar. And our first talk for this session is John van der Wetering talking to us about the ZH calculus, completeness, and extensions. John, can you share your screen and take it away?
Thank you, Miriam. Share my screen. Everybody can see this?
Yep.
Okay, great. Yeah, so I'm going to give a talk about the ZH calculus, which is a joint work with Miriam and Alex, Hector, and Sol, most of whom should be familiar because Hector was chairing the last session. But, anyway, before I get to the talk, in case you haven't noticed yet already, there is going to be a quantum pub quiz this Thursday at 8:30 p.m. European time in the Gathertown pub. You don't need to register; just show up, and we'll make some groups there, and we'll have some fun. We'll probably drink some beers, each of us in our own homes, and yeah, there is a grand prize for the winning team. So yeah, it'll be fun. Okay, so then for the talk. So I think quite a few of you will probably be familiar with the ZX calculus. And this is a graphical, universal, and complete language for quantum computing. So universal means it can represent any unitary between qubits, and complete means there are graphical rewrite rules that suffice to prove any equality of linear maps. So you can do any equality can be proven completely graphically using the rewrite rules. And the ZX calculus is great for the Clifford+Rz gate set. It is just very easy to reason about these things using ZX diagrams. But it's not so great for Toffoli. You need some workarounds to deal with Toffoli gates. And there's a variation on this calculus, which is called the ZH calculus. And this is very great for Toffoli. So it's very easy to reason about Toffoli gates. The original ZH calculus was introduced at QPL 2018 by Miriam and Alex. And this was proven to be complete for the universal fragment. So for all unitaries, all qubit unitaries. So in this work, we find a subset of the rules and a subset of the generators for ZH calculus, which is complete for the Toffoli+Hadamard fragment. So Toffoli+Hadamard, the gate set, it's a approximately universal gate set. So you can do any quantum algorithm approximately in this gate set, but it contains less matrices than the universal set. So yeah, and so that will be the first thing I will do in this talk. I will explain how this calculus works for this Toffoli+Hadamard fragment. And then secondly, we showed the original set of rules for the 2018 version actually suffices to prove completeness over any ring. So not just a universal fragment, but essentially any ring you would be interested in. And along the way, for the proof, we find a way to encode a basic arithmetic in ZH calculus, which, if people are familiar with the ZW calculus, should be familiar. Anyway, okay. So first, I want to give some motivation for these generators and the rules of the calculus, which also should hopefully explain to people who don't know what ZX and ZH is what's going on. So it's based in a sense around Boolean maps. So Boolean map is just a map that takes in a bit string and puts out a bit string. And any such map we can lift to a linear map on qubits by just defining its action on the computational basis state. So we put in a computational basis state and we output the computational basis state that like corresponds to the function application. And examples of this would be the NOT gate, which we represent by this thing. So for people familiar with ZX calculus, this would be an X spider, and it should have a pi on it, but we're going to use this negation symbol instead. And there's the copy linear map, so it copies the input, and there's the XOR, so it just takes the XOR of all the inputs. So these are things that are easily representable in ZX calculus, but not really the AND gate. So what's the deal with the AND gate? What can we do there? Well, so there's a complication there, because copy, XOR, and AND, they are all symmetric with respect to swaps and inputs and outputs. So if we swap the inputs of, for instance, the copy, we still get the same output. If we swap the inputs of two XORs, we still get the same output. Oh, just to be clear, my diagrams go from bottom to top. But there's a special thing about XOR and copy, which is that they are flex symmetric, which is a term introduced by Titouan Corrette, who will give a talk after this one. And it says that if we interchange an input and an output by applying this cup and cap, and you can think of these as sort of Bell states and a Bell effect, we still get the same thing. So it's also symmetric with respect to inputs and outputs. And this is not true for the AND gate. So there's like something special going on. So the question is, can we make AND flex symmetric? Because we would like to deal with these things that are maximally symmetric. And it turns out, yes, there is a linear map that we can apply to the output of the AND gate. And then this entire thing together is flex symmetric. So what is this linear map? Well, it is something that you should probably already know. It's the Hadamard gate. So if you apply a Hadamard gate after this AND linear map, we get something that is symmetric with respect to inputs and outputs. So then let us define this new thing, which I call an H box, which is completely symmetric in all the ways you would want. And we define it with the scalar half for technical reasons. And yeah, it's this thing. Okay, so that gives us the two main generators of the ZH calculus. In the first generator, we have Z spiders. So these should be familiar if you use the ZX calculus. You can think of these as sort of generalized Kronecker deltas. So all the inputs have to be the same, and then outputs the same set of outputs. And then there's the H box. And as a linear map, it is a matrix which has ones everywhere except a -1 in the bottom right corner. So in this sense, it is a generalization of an Hadamard, because a Hadamard also has ones everywhere except a -1 in the corner. But this is sort of a multi-legged Hadamard, which is why we call it an H box. And then there's some other generators. So we have this scalar, which allows us to take a scalar half, which is useful for our results. And sort of this, and the standard things, an identity wire, and the cup and cap, so the Bell state and the Bell effect. Okay, composing these generators, we can represent any 2 to the n by 2 to the m matrix where the entries are dyadic rationals, so z over half. So these are the matrices that are correspond to qubits, but then like a matrix the entries have to be restricted to this particular ring. And by this result by Amy et al. From 2019, such matrices precisely correspond to circuits that are generated by Toffoli gates and an even amount of Hadamard gates. So with this tensor product of Hadamard, which is an approximately universal gate set, because if I have a circuit with an odd amount of Hadamard gates, well, I can just add a sort of dummy auxiliary qubit and apply a Hadamard, and then I have an even amount of Hadamard. So this doesn't lose you anything. The reason we get it even is because a Hadamard contains a 1 over square root of 2. If we only have a half, so we need to have 2 of them to get a half. So that's kind of the reason. Okay, so this language is universal for this approximately universal gate set. So it is powerful enough to describe quantum computing. So let's see what else we can do with it. So first we derive we make some derived generators. So we can represent the X spider by just taking the Z spider and composing with Hadamards everywhere. We have this negation, this not, which can be done by applying this additional thing to it. And we have this sort of Z gate, so sort of a pi phase. And yeah, we can make this Boolean interpretation of maps inside this calculus. So we have the not gate, copy, XOR, and AND. So now we have this extra Hadamard here on this side and that side. So our rules can be motivated from this Boolean interpretation. So for instance, a copy is associative. So it sort of absorbs, if you have a multi-legged coupled, into 1. And this corresponds to this spider fusion rule. And AND is also associative. So this corresponds to this H-box fusion rule, where now we have this Hadamard in between here. If we copy just once, well, that's just doing nothing. So it's just identity. So again, a single input, single output spider is also not doing anything. AND gates, if we AND a single input, you just get the output. So it's also an identity, and that corresponds to 2 Hadamards being self-inverse, or a Hadamard being self-inverse. And the second set of rules, so this is a bialgebra rule. So these are both bialgebra rules, which tell you that you can first XOR some inputs and then copy the outputs, or you can first copy all the inputs and then XOR all the corresponding things. So this is just a Boolean identity, and this corresponds to the following rule in our calculus. And the same thing holds for AND and copy, which can be shown to be equivalent to this slightly modified bialgebra rule. And then we have that, not is its own self-inverse. And this looks slightly different here, but we can show this is equivalent to this rule in the presence of the other rules we've shown so far. Okay, and then there's one final rule we need, which is a bit more complicated. So what happens here is we have 2 AND gates, and we take an input and we put it directly into the first AND and negate it into the other AND. So that means that one of the inputs to each of these ANDs should be 0. Because if you input a 1 here, you get a 0 here, or if you input a 0 here, we get a 1 here. So one of these ANDs will have an output 0, So if we ask, are the outputs equal? Well, the only way this is possible is if both the outputs are 0. And this corresponds to this diagrammatic equality. Well, this is quite complicated, but luckily this one complicated rule is equivalent to a pair of simpler rules. So the first one here just says that if I post-select an AND gate on the output being 1, well, that must mean that both inputs should have been 1, because that's the only way I can get a 1 out of an AND. And then here it says if I copy an input and I AND it, then I just get an identity, which if you think about it for a second, makes sense. And these correspond to these diagrammatic equalities. Okay, so then we have these 8 rules. So we have a spider fusion, H-box fusion, an identity, a Hadamard cancellation, 2 bialgebra rules, this sort of simplification rule, and then this more complicated thing that we call the ortho rule. So these 8 rules, and it turns out these are complete for matrices over Z half. So this means that these 8 rules suffice to reason about an approximately universal gate set of quantum computing. So this, in principle, suffices to reason about any quantum computation that you want. Okay, so how do you prove this? Well, what we do is we reduce each diagram to a unique normal form. So we show that if I give you a diagram, I can reduce it in some unique way to some unique thing which sort of represents the matrix directly. And then if I have 2 different diagrams that represent the same matrix, then they are both reduced to the same normal form, so I have a path from one of them to the other. So I can show all these diagrammatic equalities. To do this, we need a couple of ingredients, which I will introduce now. So these are labeled H boxes, annotated bank boxes, the normal form itself, and arithmetic on H boxes. Okay, so let's get to each of these in turn. So the first is labeled H. An H box has ones everywhere except a -1 in the corner. And we want to generalize this to having a 1 everywhere and then some other element in the corner. So we have the standard -1 here, and then we have the 0, which is just this X spider. We have the 1, which is just this Z spider. And we extend this to higher arity H boxes in this way, sort of by using this unfusing of an H box. And the nice thing is we can build higher numbers from lower ones by sort of this successor function. So if we apply this gadget afterwards, which for those familiar with it is equal to this triangle generator from the ZX calculus. So we can build higher number labeled H boxes this way. And so by continuing this, we can build all natural numbers just by starting from 0. And we can build negation, so by applying the Z gate to it, which negates the number. Okay, so those are labeled H boxes. Another thing we need is bank boxes. So bank boxes have been around for a while for the ZX calculus. And it allows us to represent an entire infinite family of diagrams. So for instance, here we have a bank box around this thing, which means this represents a family of diagrams where what's inside the box is repeated some amount of times. So here it's repeated 0 times, here it's repeated 1 times, 2 times, 3 times. But what we actually need is a variation on this, which is called an annotated bank box. So here, instead of representing an infinite family of diagrams, it represents just one diagram. But sort of it tells us how many times to repeat what's inside the box. So here we have this set of Boolean bit strings of length 2 Boolean bit strings. So what's inside here is repeated 4 times because there's 4 Boolean bit strings. And what's nice now is we're allowed to annotate stuff in this box. So for instance, we have these 4 values and they're allowed to be different. This is sort of a compact representation of a large diagram. And what's useful additional notation that can be combined with this is what we call an indexing box. So this allows us to define sort of a combination of identities and not gates. So we can sort of negate just some of the wires. So this bit string tells us which of the wires are negated. Okay, so we can use this to define our normal form. So for that, we require this thing called the Shear product. So if the Shear product of 2 quantum states, it's just an element-wise product. So if I have 2 qubit states or 4 elements, I just multiply each of these 4 elements in turn. And this is represented in this way in our calculus. So just applying these Z spiders to each of the entries in turn. And then our normal form is built by doing this Shear product on an exponential amount of input states, so 2 to the n input states. Namely, we take this labeled H box, which has ones everywhere except A00 on the bottom right corner. And then we apply this indexing box, which applies a knot to some of the wires. And the action of this is that it moves this single non-one element around in the state. So it moves it to a different location than the last position. And then we take the shear product. So then all these things are multiplied together. And that means that this thing represents a matrix where the elements are precisely these A00 and A01 and A11. Like, so this can represent any matrix sort of uniquely. And yeah, we have these stars here in order to represent halves. And yeah, in order to have a unique normal form, we require that this number k is sort of minimal given all these odd elements. So either k is 0 or one of these is odd, because if one of these were even, then we could sort of take out a factor 2 inside these stars. Okay, so that's a normal form that we're reducing to. So then the majority of our paper is showing if we can in fact reduce diagrams to this normal form. And the way we do that is we show that each generator can be reduced to normal form, that tensor products of normal forms can be reduced to a normal form, and that any wirings of a normal form is reducible to a normal form. So then if I give you a diagram, I can just decompose it into a tensor product of generators which are wired together in some way. So then I first write each of the generators as a normal form, then I tensor all these normal forms and make them into normal form, and then I take these wirings together and also reduce it to normal form. So this gives us a way to actually reduce any diagram to normal form, which is yeah, this is the difficult part. Yeah, and to do this, we need to be able to do arithmetic on HBox labels, which is a thing I will say a bit more about. So we can do addition on HBox labels. So if we have this little gadget here, this little diagram, and we input these two labeled HBoxes, we get out the sum of them. And we proved this using induction essentially on sort of base cases. And we can also define multiplication, which is just by applying them both to a z-spider. And we have this thing average, which is useful for our proof and will also be useful in a few slides, which is sort of, we add them together and divide by 2. This is sort of like, this is the multiplication gadget, and this is sort of the multiplicative inverse. So this is sort of multiplying by a half. So we get sort of the average of these two. And we have this rule, which is not really arithmetic, but it's really useful. We call it introduction, because what it does is it introduces new legs to existing HBoxes. So we introduce sort of a new wire to this HBox here by sort of pairing these up. And the way this, the reason this holds is we have sort of an input computational basis state, and it goes directly here and via negation here. So it applies in exactly one of these cases and sort of multiplies the state by A. And so it doesn't matter what the input state is, you just always multiply by A. So that's kind of the reasoning behind this rule. Okay, so to summarize, we have these 8 rules, which are motivated from sort of Boolean functions. And these are complete and universal for matrices over Z1/2, which is an approximately universal gate set for quantum computing over qubits. So these 8 rules suffice to do graphical reasoning over quantum computing. Okay, so now comes the second part, which is generalizing this result, not generalizing, but modifying this result, so that we can represent more types of matrices. So not just matrices over this ring, but over more general rings. And the way we do this is by promoting these labeled HBoxes to actual generators, not just sort of defined in our calculus, but actually make them actual generators. So we start by picking a commutative ring R. So this can be any ring R, where as long as 2, so just 1 + 1, has an inverse of half. So for instance, the ring Z, just the integers wouldn't be allowed because 2, it doesn't have an inverse, but the dyadic rationals will be fine. And then we define this generator for any element in this ring, which is just an HBox with the R on it. And we just define it in this way. So this will be a matrix which has 1s everywhere, except there's an R in the bottom right corner. And these, again, using the same normal form, essentially, we can show that the resulting ZHR diagrams are universal for matrices over this ring R. Okay, so these can represent matrices of any ring. And then we find an extended rule set. So we have the rules that I showed before. So we have the spider fusion, HBox fusion, identity, Hadamard cancellation, the bialgebra rules, and this ortho rule. But now we've sort of made the HBox fusion a bit more general, and that we can fuse with arbitrary labeled HBoxes here. And we promote this multiplication, average, and intro to actual rules instead of derived equations. And then we have this identities to sort of relate the ring elements to the spiders. And it turns out that these rules are complete for matrices over R. And the proof is essentially the same as the one where there are no parameters, which is just we reduce to the same normal form. And the reason it works is because now these things that we actually had to prove, these multiplication, average, intro, we now assume as axioms. Okay, so what happens if 2 does not have an inverse? For instance, if we have the integers. Well, that's a problem because we had this generator, the star, which is equal to a half, and we don't have this half now, so we need to do something else. What we can do instead is we can promote these X spiders to actual generators instead of being derived generators, because their definition required this star, which we don't have access to. So we define it this other way. And then it means that we need to promote their what was used to be their definition sort of to a new rule. So we have these rules that relate the Z spiders and X spiders. And in the other rule, we had like a star here, but now we've sort of taken the star to the other side and it becomes this legless Z spider, which is a scalar 2. So this is still a sound equation. So we have these new rules. And we need a new meta rule because we don't have the star, but we still need to be able to sort of reason about scalars. So what we say is that if we have a diagram equation where there is this scalar Z spider on both sides, so this value 2, we can cancel this value to sort of get this diagram equation. So we need this to be able to reduce to a normal form. But this, we need to note that this meta rule is only sound when 2 is not a zero divisor. Because if 2 is a zero divisor, this equation could hold, while this equation does not hold. So now we're working with any ring where 2 is not a zero divisor. And it's also necessary for a proof, because if it's not a zero divisor, then the ring embeds into a ring where we add a half sort of freely. And then we can reduce to our previous proof. So that's sort of a technical condition that we need there. Okay, so then we get a theorem that if we have a commutative ring R, where 2 is not a zero divisor, then the rules I've just shown you, plus this meta rule for scalar cancellation, are enough to make ZHR complete for matrices over R. Okay, so conclusion. I presented a new small and complete axiomatization of Toffoli+Hadamard circuits, which has a clear relation to Boolean circuits. And this is straightforwardly extended to a completeness result for almost arbitrary rings, which includes the universal fragment for quantum computing. Yeah, that's what I want to say. So thank you for your attention. And if you want to check out the paper, well, you can find it here.